Why seven colors?
Red, orange, yellow, green, blue, indigo, violet. That neat sequence feels solid, almost unquestionable. We repeat it in school, we see it in textbooks, we teach it to children. 7 colors fixed, defined, but the sky does not read textbooks. The rainbow above you is not divided by lines. The idea of 7 colors is something we inherited, not something nature strictly enforces. A rainbow begins quietly with sunlight and suspended droplets of water. Sunlight looks white, but it carries a spread of wavelengths across the visible spectrum. When that light enters a raindrop, it slows down and bends. This bending, called refraction, happens because light changes speed when moving between air and water. It is subtle, but it is the first step toward the arc. Inside the droplet, some of the light reflects off the inner surface at the back. It does not escape immediately. Instead, it bounces once and then heads outward. As it leaves the droplet, it bends again. 2 refractions and 1 internal reflection reshape a straight beam into something structured and ordered. Physics begins to carve pattern out of sunlight. Not all wavelengths bend equally. Red light, with its longer wavelength, bends slightly less. Violet, with its shorter wavelength, bends more. That small difference matters. After reflection and refraction, red light exits the droplet at roughly 42 degrees relative to the incoming sunlight, while violet exits closer to 40 degrees. That narrow angular spread creates the layered arc we recognize. Now multiply that process by millions of droplets. Each droplet sends only one specific color toward your eye, depending on its position. You are not seeing one object. You are seeing countless tiny optical events aligned precisely with your viewpoint. The rainbow is not located at a fixed distance. It exists in the geometry between you, the sun, and the rain. From the ground, the rainbow appears as a semicircle. From an airplane, it can form a full circle centered on the anti-solar point. Directly opposite the sun, this geometry is exact and predictable. The curve is not symbolic. It is the mathematical consequence of light interacting with spheres of water in a 3-dimensional space. So where do the 7 colors come in? Physically, the spectrum is continuous. There are no natural borders where yellow ends and green begins. The visible range spans approximately 400 to 700 nanometers in wavelength. Within that range lie countless subtle variations. The separation into named bands is something our minds impose for clarity. The association with 7 colors is strongly linked to Isaac Newton. In the 17th century, Newton used prisms to demonstrate that white light could be decomposed into a spectrum and recombined again. His experiments were rigorous and repeatable. He showed that color was not created by glass but was already present within light itself. When categorizing the spectrum, Newton initially described fewer divisions. Later, he expanded the list to 7. He was interested in harmony between natural phenomena and musical structure. The 7 notes of the diatonic scale influenced his thinking. By adding orange and indigo as distinct categories, he aligned the spectrum with a culturally meaningful number. Modern optics does not require 7 divisions. The light itself does not contain labels. Different cultures have described rainbows using different numbers of colors. Some traditions group blue and green together. Others omit indigo entirely. Linguistic research shows that color categories vary across languages, even though the underlying spectrum is the same. Biology adds another layer. The human retina contains 3 main types of cone photoreceptors, each most sensitive to a different region of the spectrum. These are commonly referred to as long, medium, and short wavelength cones. Our perception of color arises from comparing how strongly each type responds to incoming light. The brain does not read wavelength directly. It interprets ratios of signals. A particular combination of cone responses is translated into the experience of blue or green or yellow. Because this system is comparative and continuous, the boundaries between colors are not physically embedded in the light. They are constructed categories that help us organize perception. That is why indigo is controversial. Many people struggle to identify a clear, separate indigo band in a natural rainbow. The transition from blue to violet often appears gradual. Whether someone reports seeing indigo can depend on training, expectation, and language. What we are taught to look for can subtly influence what we believe we see. Environmental conditions also shape the display. Larger raindrops tend to produce brighter, more sharply defined colors. Smaller droplets create softer, more blended arcs. The sun's elevation affects the rainbow's height in the sky. Near sunset, the arc rises higher and can appear more expansive. The phenomenon follows precise optical laws, yet no two sightings feel identical. Sometimes a second, fainter arc appears outside the first. This secondary rainbow forms when light reflects twice inside the droplet before exiting. The extra reflection reverses the order of colors and spreads them over a wider angle, making the arc dimmer. It is a reminder that even within strict physical rules, variations emerge naturally. In the end, a rainbow is both exact and interpretive. Refraction, reflection, and dispersion govern its structure with mathematical precision. Yet the way we divide and describe its colors reflects history, language, and perception. The familiar sequence of 7 colors is a useful simplification, but it is not a boundary drawn by nature. So the next time you see a rainbow, don't just look for the 7 colors you learned in school. Take a moment to appreciate the seamless, breathtaking gradient of light. Recognize that you're witnessing a continuous spectrum of millions of colors, a beautiful interplay between sunlight, water, and your own perception. The 7-color rainbow is a wonderful simplification, but the reality is infinitely more complex, and I think even more magical. Thanks for watching. If you found this as fascinating as I do, hit that like button and subscribe for more deep dives into the science behind our amazing world. See you in the next video.